Okay, so yeah, so you're going to want to do those because we're going to have problems, but I'm going to do some reviews, and I'll actually post something like a practice exam this time. Like I did last time, I posted something, but this one should be better. Because this part is really important, but it's not as complicated. Question?
Will there be anything from the last exam?
There could be something like K-maps on there, because K-maps will haunt you for the rest of your digital engineering career, unfortunately. Not really, they're kind of fun to me, but we want to make sure that we understand things like timing diagrams, especially. So I printed out some past exams that I've actually used for reals before, and that's where I'm going to pull these example problems from.
Sponge the analog accuracy.
Boring stuff. No, just kidding. All right. So I'll just pull out one of these exams and give you guys some examples of things. So here's a nice, easy question. Come on. There we go. Okay. I give you this picture. What is this device? Yes, that's our flip-flop. But it has a little thing on it. If I instead replace this with like an enable, then it's an SR latch, right? Clock flip-flop, not clock latch, right? In fact, I think that's one of the other questions I have on here. Is one of the other exams is, what is the difference between a latch and a flip-flop? And one of the answers is the flip-flop has a clock input, right? It's as simple as that. Flip-flops are clocked. If I give you, so we've started talking about processes, right? And we started designing some processes, or at least you should in 12, chapter 12, which is how do we design flip-flops, right? Things with memory. So if I were to write something like process on a clock, right? This is a sensitivity list. Begin. I heard it, if rising edge, right? I need this, otherwise it's not going to work. If rising edge of clock, then do stuff, right? And so like if it's a D latch, if there's a rising edge of latch, then Q could get assigned to D. Right? I've made the world's simplest D flip-flop. Right? Because I have a clock signal that is taking something called D and putting on Q. You should be able to do something like, remember that if I add a sensitivity list on the reset, have I talked about resets much? I don't actually remember. It's okay. Anything else I add on reset is going to trigger this process. But if the reset changes, this won't change. So the way we tend to use those resets, which we'll get into more after the exam, is slight change if reset equals 1. So this is an active high reset, right? Then Q gets assigned to 0. Else if rising edge of the clock, Q gets assigned to D.
That reset is asynchronous.
Yes, that's what I was getting at. So this is an asynchronous reset because it does not depend on the rising edge of the clock to trigger, right? It's in the sensitivity list. Therefore, if it's 1, process will evaluate, run, determine the if, do the Q. So then, this is called sequential logic, right? I've used that whole word a whole bunch, sequential. Over here, I'm going to write combinational, which is something like a mux, right? right? Boom, I made a mux.
What does process really mean? Because right, you can have like a process and it's combination only stuff in the process, right?
Yes, yes. However, they're slightly different. So I can design a mux also with a process, and it can be sequential. So this is also a mux, right? It looks at the select and assigns A to M or B to M. This is still combinational logic. It is combinational logic. A process is still combinational logic if all of the inputs are in the sensitivity list. So if any of the inputs can change it, more specifically, if all of the inputs could change it, then it can be combinational logic. If any of the inputs, in this case D, right, is not in the sensitivity list, it must be sequential. Okay, what is a big difference in the way that a combinational statement executes versus a sequential? So like if I have this and then I do something like another signal just does that, right? What order do these run in combinational logic? The same time, right? They're always running at the same time. Combinational, it runs in parallel. Sequential runs in sequence, one line after the other, right? That's why it's called sequential. Okay, keep those straight. Remember the word sensitivity lists. Make sure you keep track of, and homework 12 will reinforce this. I know I've talked about JK, D, and T flip-flops, right? And we've talked about how we can build like a timer or counter off of a T flip-flop chain really easily. I could have questions, let's see. Yeah, so I actually have another question in here that I give you some VHDL that goes through basically this, and it asks the question, is this reset synchronous or asynchronous? Right, and it is asynchronous. Right, because synchronous means it depends on the rising edge of the clock, okay? If the reset doesn't care what happens to the clock, it's asynchronous. If I do, so let's see how I did this. If Q is my output, right? And I wanted to have some enable, right? An enable signal that either turned on the Q or didn't turn on the Q update. I could do something, you can imagine that I could do code that would have an embedded if, right? This is just layered if enable equals 1, Q gets assigned to D, else Q stays Q, right? What is a major reason that this might not work? If I were to try and build a module that is supposed to be a D flip-flop with an asynchronous reset and an enable, why might this not work? Well, that would work fine. So let me draw the next bit of information you might need that might help you make the leap. So I have the entity, right? And it has ports of, sorry, I don't remember how to do this. Where are they? Just Q, cell, enable, oh wait, Q's not input, D, that are in the standard logic, and Q is an output of also standard logic. Does this code work to implement that entity? Just one rule that I've told you guys multiple times that I'm hoping you look for.
Because the Q's at the right side.
Yes, thank you. You cannot put an output ever on the right side of an assignment statement. That's
Made a buffer would have worked.
yes, but I haven't talked about buffers as a state, so that's and I don't recommend using them because they are a really good way to ruin everything. What is the right way to fix this? Yes, and create an intermediate signal called like Q underscore S or something, right? And then we can assign QS to QS. That works. And then outside of the process, then I can just say combinationally, Q gets assigned to QS, where this gets replaced with QS, right? That makes it so that we don't have to have an output on the right side, which is never allowed. This was actually one of the questions that I asked on the last exam. The difference is I gave the code and then I asked the question, why did I do this intermediate signal, right? And it's still looking for the same idea, is I cannot put an output on the right side. Okay. I can ask any types of questions that I think you guys should be familiar with. So I could happily ask this is a very simple entity, right? I could ask, say something like, given this entity, write VHDL to implement a Q flip-flop. Or sorry, DQ flip-flop, right? That's fine. I won't ask you to do anything much more complicated than that. Try and write the code as correctly as you can. It does not have to be spot on perfect, right? But like, unless I say otherwise, things like if you forget a semicolon, I'm not going to judge. Probably even forget, like if you put the colon in the wrong spot, I'm not really going to judge, right? Things like that that are minor. Not going to miss any points unless I specify, like be very careful, right? But most, because one that might make you be very specific is if like I gave you this line and you had an exact right answer to look at, and I said now make the outputs or something like that, then I would expect even more right. But I don't expect you to have VHDL perfectly memorized because well, I don't have VHDL perfectly memorized. But this is acceptable, right? Where the important things are taken care of, this is an equal comparison, whereas this is an assignment, right? Make sure those are correct. Notice that I said n is 1, I forgot the ticks. If I'm asking you to draw code from nothing, forgetting the ticks is probably okay. But if I give you the code and ask you something like, find the errors in this code, right? That is also a fair question. What is wrong with this code? And the way I usually ask those is I would do something like I would make 6 or 7 errors and ask you to find 5 of them, right? So I don't expect you to know all of them, but you should be able to find at least many of them, right? So you would go through and be like, okay, well, that's a bit type, we forget a semicolon, else if rising edge of clock, I forgot a then, I forgot the apostrophes, I forgot a semicolon, I forgot the end ifs, right? Things like that. That would be the kind of example. This would actually be a perfectly fair question to have asked, is given that code, correct the errors. Question?
Oh, I was just gonna say, when we write VHDL code, do you care if we use like shorthand, like 7 arrow down?
Not at all. That is any shorthand that I use, like RE is perfectly allowed. A down arrow for down 2 is perfectly allowed. Things like that. Make sure that you understand that if I give you 2 entities and one of them has 7 down to 0, right? And this is a port, and then I have a signal that is 6 down to 0. That doesn't work, right? It's unhappy. Make sure that you understand the port map matching. If I were to say, give you two entities or component declarations, say, I'm gonna give you two component declarations and tell you to imagine that you're writing the top level module, connect these two together, write the signals and the connections that you need for write the instantiation and any signals that you need to make them connect, right? So I might, for example, the dumbest way that I could do it is I could give you guys a full adder component and say, write a top level module for me that uses this full adder to make a 2-bit adder, right? And then you would write the component instantiations, write two of them, you create an intermediate signal, ta-da, right? That takes the carry out to the carry in. So asking you to implement components that maybe you don't even know what's inside of them, but you should know how to connect things together to achieve the goal. So this is another kind of important one. I think this one is in the homework as well, and I ended up putting on the test, is given a DQ flip-flop, make a clock enable. Given this DQ flip-flop, I want you to build extra circuits around it to make a clock enable. And we talked about two ways, right? One was bad, one was good. This again will be open notes, open book. There's a hint on the board.
I have using Lux in my notes, but I'm not entirely sure because I don't think it's a clock enable. It's just an enable. It's not connected to the clock.
Turns out it is a clock enable, actually. Yeah, it's actually exactly what this is doing.
Because you have to remember the clock enables D, so anything you're throwing into D is going to be.
Yeah, exactly. So what you can look at here, so here I said this is a mux, right? Well, it turns out this structure is the same thing where we're using an enable on the mux. It just, we turned it into a synchronous mux. So the wrong way is that, right? That is a clock enable, but it has issues. What are the issue?
It doesn't know the difference between enable and the rising.
Yes, it doesn't know the difference between a rising edge of an enable and a rising edge of a clock. It has no way of differentiating. So we don't like to do that. We just like to put the clock directly in. We do the mux, just like you pointed out. And in one case, this is now a clock enable, right? Because if the rising edge of a clock happens and we're not enabled, we just take whatever Q is and put it back onto D. There's no update. Whereas if enable is true, then we take whatever's on DN and put it into D and we do update. I have a whole page. This one is kind of fun, where I give you code and ask you to name the device. And these devices are going to be things that we've talked about, things like a mux, things like D flip-flop, JK flip-flop, SR latch, D latch, right? Any of those devices we talked about, I might give you code for and ask you, what is it, right? This is the same thing as that I already mentioned, right? What is this device? I've written this code. What is it? What is it doing, right? The next big thing that we're going to have to deal with, and you'll get lots of practice in this on the upcoming homework, is timing diagrams. So I already had you guys go through one of those on the last exam, and you did actually fairly well. This one's kind of difficult. Right. Yep. So the question that I gave to the last class is actually harder than what I would do to you by a little bit. And not because I don't think you guys could do it, but because grading it turned out to be a nightmare. But the question that I asked for this one is, given this circuit, exhaustively provide a timing diagram that exhaustively tests it. And so I haven't quite used those words with you guys yet. And so I provide a diagram that looks like this, right? Much like I did with you guys before. It has A, B, C, and I called this D, B tick, right, for B naught, just to be explicit, F, H, and G. And then ask the question to be, exhaustively test the circuit. Now, you've seen this word before, right? It's just been a little while in your homework. It was the earlier questions were like prove De Morgan's theorem by exhaustion or something. All that means is do every combination of inputs. Okay. The difference is now when I write these exams, I actually provide the input waveforms because it turns out it's really difficult to grade if some of you use this as the least significant bit and some of you use this as the most significant bit. So I hate that. So what I do now is I say something like, given given this, finish the timing diagram, and I would have a B, C, E, G, H, okay? And I would ask you to finish this timing diagram. And right, the way you do that is just one at a time. B naught is really easy. It's just the opposite of B. And I will usually provide like dashed lines vertically. Sometimes I forget this, right, to kind of help you mark it. If I don't provide them, draw them. Like anywhere something changes is an interesting point if it's combinational. If it's sequential, we only care, the only interesting points are the rising or falling edge, whichever we're looking at in the code, right? So B is just not B is the inverse of B. D is the NOR operation of B NOR C, right? And if you need to, there's nothing wrong with going back and reminding yourself saying, well, if I have B or C, my OR is that, right? This is OR. I know, I'm getting there, right? Because a lot of times it helps to start with OR and then just invert that to
Well,
NOR.
I'm saying is you wrote the NOR instead of the OR. It should be 0, 0, 0.
Oh my gosh. I wrote NAND actually, right?
Oh, yeah.
I wrote NAND, not
I wrote NAND.
Yeah, thank you. So OR is that, and NOR is just the inverse. So now I can know that I am asserting a 1 if and only if I have 0, 0 on B and C. So I can go back to this timing diagram and say B is 0, C is 0, B is 0, C is 0. So D is 1 until that point, and then nowhere else am I going to have that combination, right? I don't see any other 0, 0 for that, so we're going to drop and move on. And then when you get to G, now G is just OR of D or C, but make sure you do D or C, right? Don't go all the way back to B, right? Don't think of G as B nor C or C, right? Just, which actually, we're just gonna worry about G is D or C. So now I go look at D or C. And if they're one, if either of them is one, it's true, right? So one here, and then we get one here, so something like that. Right, I just worry about D and C. This is good for grading because all I'm gonna do is when I get to F, sorry, when I get to, oh shoot, that was G, not F. Right, sorry. When I look at G, I'm not gonna look at it as B nor C or C, right? I'm going to look at it as D or C. So I'm going to look at D or C. If D is wrong, but G is right, you get points. But if D is wrong and you try and base it off of, even if D is right and you base G off of B nor C and get this wrong based on what your D is, you're still missing points because I'm not looking at it all the way back. I'm just looking at it as D or C in terms of the intermediate signal. You should think of it that way too, because there's no reason to add any complexity past that. This is a question that I'm going to post. This is harder by far than what I would do to you, to be honest. This is like one of my favorite exam questions I've ever written, but it was also way too hard for an exam. Okay, so the question here was, and I'll give this to you guys as part of the study because if you can do this, you'll be fine. But the question here was, given that Q0 and Q1 are both 0, at time 0, finish the timing diagram for, well, what I gave was J0, K0, for these signals. So where the J0 signal, so I'll start with the K0. K0 is Q1, right? Because the Q1 feeds back to K. And then the other one, J1, is here is Q0, right? And so J0, K0, J1, K1. So the signals that are going into those finish the timing diagram. Sounds hard, right? Well, it's a JK flip-flop. We remember what JK flip-flops do, right? Is we're going to talk in terms of Qn plus 1, right? What is the next Q that's going to come up based on the J or K?
This one's not that bad because we're only in the set or reset state. We're never in the, right? Because we can never have J and K both at the same time.
Well,
Like
yeah,
Q1,
let's check that one. Sorry, I need to finish this. This is, we state Qn. This is the, well, you know, what is this one?
That's reset, right?
Set, reset, set, and toggle.
Never toggle, right? Because Q and Q naught can't both be true at the same time. And that's the only way we can have J
Yeah.
and J.
Yeah, so, well, this one will never, and then that one is the opposite, so it will never, correct? Yeah, so, right, so what you can do is start looking at what happens at each of these points. So you can easily start with, well, I specified that Q naught is 0 at time 0, and Q1, which makes, so this is 0, this is 1, and so you can go to J0, K0, and start, sorry, J1, K1, which is J1 is 0, which makes that 1, right? And then I start looking for rising edges of clocks and using the inputs of, well, what is the JK input? What does the output do when it sees that rising edge of a clock? Well, if it's 1, 0, or sorry, 0, 1, 0, 1, it sets Q1 to 0, okay? And then you do QR that one, feed it back around, and just kind of step through. Now, this one is very hard to do. I'm not going to do it because I'm going to make you guys go through this pain. But what's nice is if you can do that one, your timing diagram skills should be up to par for what I will actually ask. So, good practice problem is harder than the actual test problem, right? This question is right out of the notes. The next one is, draw me a 3-bit synchronous counter using T flip-flops. Right? Talked about it in the notes. It's T flip-flops, just toggle. That might work. I don't remember. Right? We just have to figure it out. Because if enable is true, then the output is going to toggle. And so here I would have 0, and let's say I'm starting at 0, 0. Oh, this one doesn't quite work right. I need a feed forward path as that AND gate that we talked about in class. This is your note. Just know how to build a basic counter out of T flip-flops. I could throw it around and do like give you something that was T flip-flops and be like, does this count kind of thing, or give you, for a good example actually that would be different than this example would be to given these D flip-flops, this is supposed to be a counter. Finish the timing diagram to determine if it works, right? Or finish the timing diagram and tell me if it's an up counter or a down counter. Here's an example code that I talked about. I'll just point it, I won't pass this around exactly, but be familiar with the HDL code because this is an example where I said, actually, I will probably have enough time that I can put this on the overhead projector. Actually, maybe. Okay. Yeah, so it's code that is there. It says there are at least 5 errors. Find in the code below. Find and fix them. Let's see. I do have a document camera, and I'm going to see if I can make that work. It's acting like it's trying to work.
Yeah, I know. But it was just moving around.
Okay, so if you end up going back and re-watching this, it looks like I accidentally turned off the camera there, but it's back on now. I'm going to have to I'll just post the code online. I guess I'll have to post this code to make this review fair for people that don't make it. But we'll walk through kind of how I would do this kind of problem. Okay. So as mentioned, right, consider the following code. There are at least 5 errors in the code, but none of them should obfuscate the code's intended design. What that means is you should be able to tell what this is supposed to be able to do, right? I didn't break it that far. Find and correct 5 errors in the code, and then you're going to draw a complete block diagram for the code. This diagram should include a top level and module level ports and connections. So this is, I keep harping on, you guys should be able to draw block diagrams. This is a very important skill to be able to turn pictures into code and code into pictures, right? Going back and forth. This is how I debug everything. This is how I design everything. I don't know about a better way. All right, so the first one I'm gonna do, unless I say something, which I won't for you guys, my 3610 I do this, but for advanced, I won't use things like semicolons and failure to ends. With you guys, I will, right? Most of these are going to be simple syntax errors that you should be very familiar with. And what I'm going to do is the first thing, I'm going to look through and see if there are enough ends. I'm also going to, on the first pass, check for any missing semicolons and any missing ifs, thens, or rising edge of clock, right? Those are like the 4 big things that I'm looking for. So I'm going to go stand back here so I'm not in anyone's way. And let's go ahead and look and start just going down. I see semicolons. If anyone sees an error, let me know. Missing, what am I missing on the first port? Ah, yes, I am. So the first one pointed out, I haven't looked at this in like a year, so I actually don't know, is that parentheses.
On the next line down, it says end component, end after sub.
Yep. And that's just make sure that you guys write end adder sub instead of end, or is it end, I don't remember, end entity, whatever the right one is. Let's go down. I see a missing semicolon here, right? That's the second row of the subtractor. Yeah, I got a couple left that I see. Line 30 needs a comma. So we've got 1, 2, 3, 4 errors that we found and corrected. The way I designed these, there should be at least 1 or 2 more. Or sorry, there should be at least 2 more because we only have 4. I should have 6 in here somewhere. Bit eyes. Yep. There we go. We got 5. There's probably at least 1, likely 2 more errors in there. That's usually how I do it. Question?
No, I just like to try and find it.
Oh yeah. Sometimes what it'll be is like I don't think I did it here, but like in the component I've declared 1 down to 0. We want to make sure that when I apply this adder, here's the adder, is my signal A and B both 2 bits? They are, yay, right? But I could theoretically make an intermediate signal of the wrong size to try and connect things together. So that's my next pass, is things that are more in detail of like, are the sizes right? But I like to start off with things like semicolons, ends, right? So here I don't actually see any other ends, but we got that one end component. This is an end component, that's end component, end component. And then we would want to make sure that like if there was a process, we say end process. I'm pretty sure this is supposed to say end. Where's the architecture? End adder sub, right? That's the next error. Do you have a question? Oh, was that what you saw? Yeah. Yeah, that's the other error, is this is the wrong end. So that's the kind of things that you can hopefully find and expect to find. The next step is to draw a block diagram of this. Okay. So there is a top level module that I'm going to draw last because I don't know how big it's going to take. But I know that I have this component called adder, a component called subtractor, and a component called mux bitwise. Okay. So I'm going to just draw those subcomponents. And I'm going to call this one add 0 and this one sub 0, right? Because that's the actual instance name. It is not adder. Adder is the type of component. The name of the component is add 0. Okay. And then I'm going to go look and see how they're connected. So port S1 is an input, and it goes into A. S2 comes from a signal called B. And that same signal A and B come from sub 0. Now, this is actually a little bit of a trick to make sure that you recognize that both of these are perfectly fine ways to create an instance, right? Explicitly mapping it and positional mapping are both fine, right? We prefer this one. There's way less errors that you're going to run into, but we prefer it. So I have a signal A, a signal B. I'm actually just putting it up here. B, A, and B both go into ports. S1, S2 are the name of this one. And then in the case of the subtractor, they're D1, D2. Right, so I plug A and B into S1, S2, and D1, D2. Just like that. Okay, the next one is the outputs are called sum and diff. The ports are also sum and diff, so the port name and the signal name are the same. The signals sum and diff go into the inputs, A and B, of a mux. Mux also has a port called S, and its output is S or D. Okay, now I've connected all three of those together. Now I need to point out that I have a top level module that goes all the way around them. This top level module is called add or sub. And now it has ports A, B. So I can just extend those to the port. And S and an output called S or B.
Trying to wire B to an output, so that's an error too, right? The map to diff, because diff's on the right side, and it's an out.
B.
Port diff of
Of
subtractor.
diff. Diff is an output of here, but input to the mux.
Okay.
So that's diff. This signal is called diff.
Oh,
The port is called diff. This signal is called diff. And this port is the mux's port, which is port B.
That's what I was thinking.
Yes. Another error, right? Is I need that intermediate signal. So that would make set, let's see, 1, 2, 3, 4, 5, 6, 7. Oh, looks like I was nice and did 8. Tried 8 errors in this one. So what I always do to make these is I generate working code and I just change things.
There should be another one for some.
Yeah, there should be a, what is actually interesting here is I'm missing both. I have the signal diff, I need a signal sum. So explicitly. Okay, block diagram makes sense, right? And what's nice, this question, this is basically just one portion of project 1, right? This ties into project 1. I do that very often where I'll ask questions that relate to the project or labs that we've done recently. All right. Ow, don't turn off your camera.
Is it on this thing?
It is. The camera one is its own. The camera one is narrow enough that it turns on only the camera. But the projector one turns on or off both of them.
Oh, nice.
Yeah, super nice. So if the video, I don't know, if the video cut out and you're watching this online, you heard all the words, this is the picture that I ended up drawing. You can go through the practice and email me if you think you got it right or you have questions. Okay. And what I just went through were most of the problems other than like the short answer conceptual ones the true or false, right? I usually start with true or falses. I have a couple of those just to check in to make sure you were paying attention to things that I say. But that's the sample exam that I just walked through is all of the more difficult problems of one exam. I will post a sample something or other, and I'm also going to take a peek. I have another exam and see if there's any other questions. This one had a timing diagram for an SR latch, right? It has that cross-coupled NAND gates. Remember way back at the beginning, right after the last exam, I think is when we did that one. That's funny. Sometimes I make mistakes, but this is a good question. So true or false, the order of concurrent VHDL statements may be changed without affecting the way that the model functions. True or false?
What was the question?
The order of concurrent VHDL statements may be changed without affecting the way the model functions.
True.
True, right? Concurrent, combinational, same thing.
That's the case just because VHDL doesn't really care.
Because hardware doesn't care.
Right.
Yeah, because in hardware, concurrent or combinational means you have like parallel data lines, right? Like multiple AND gate networks kind of thing. Okay, this one is actually multiple choice, but I'm going to make you guys just answer it without seeing the options. A flip-flop requires its input to be stable for some amount of time after the clock edge in order for it to work properly. What is that time called?
Is it TH, time needed to hold signal?
Yes, hold time.
Hold time.
Yep. right? So we've talked about propagation delays, setup times, hold times. Answer D was lunchtime, which is clearly not it, but
What
I
is?
I would want to answer that. It's a attempt us to answer something. I was like,
yes.
Is time setup previous to the rising edge?
Yep.
So it's not, okay.
How much time do you need your data line to be set up before the clock hits, and how long after is it there? Do we
Okay.
get to hold it?
Okay.
This exam asks for a timing diagram of a T flip-flop, which is way easier than that weird JK flip-flop mess up here, right? That's harder than I would do as I
Is it
assume.
set time to like build a charge on like the one side of the gate so you have like enough to activate the next?
Sorry, say that again.
Like set time, like I'm trying to understand why you'd have to have a set time. Is it so
Oh,
like
it's setup
the-
time.
so you can build charge on one of the gates to activate the next, and then like the whole time is to get enough charge on the
Not
other gate to activate.
Really, I mean, there are considerations around the charging and delaying that correspond to this, but the ultimate answer is when I give you a clock, I draw them like this, right? But as I've mentioned multiple times, a real clock looks more like that. And the slope of this line is there, and worse, we don't actually know when that's going to happen. So we have a rise time and we have what's called jitter. And so that's what starts setting our propagation delay is we are set up and hold time is we don't actually know when this clock is going to happen. So we need to make sure we're outside of the jitter and the rise time issues.
But at least the rise time is due to the
Capacitance. Yeah.
So it's like a product.
Yeah. It's results of the device physics, but we're going to focus on it as signal right now, right? Because that's kind of what we do as engineers is we start you guys out fairly abstracted and then we delve in a little bit deeper and then we kind of come up and extract and delve deeper, right? That's just the cycle.
When we do the timing diagrams, do you just want us to assume that it's like a perfect world? It does it right on that edge, or do you want us to?
You can't because like the
Yeah.
toggle one won't even work if you do it right on the edge because you don't know. You can't do it right on the edge because like what is that? Is it high or low right on the edge?
Yeah, so give it a smidge of delay just because it will keep your life simpler. But at this point, because we've talked up as setup and hold time and clock to Q delays, right? I've talked about those, is I could have a flip-flop where I could give you a timing diagram and say this has a setup and hold time of blank nanoseconds, 10 nanoseconds, and a clock to Q delay of 20 nanoseconds or something like that. Draw the timing diagram, right? And if the rising edge comes at a time I'm just gonna start erasing stuff. I give you a DQ flip-flop, and I say your D input something like this, and I would say, assuming the Q starts at 0, finish the timing diagram, right? And I would give you like lines, vertical lines that help illustrate where the times were, so you would have to kind of guess. But right, the first thing that you would do is you would pay attention to important locations. If there are only 3, if this is a rising edge device. And I would go, okay, well, I'm 0 up until here, and then something happens. But almost no matter what my setup and hold times are, this is in violation. So my result is I don't know what that is, right? That's
Are
what
those
happens.
supposed to be lined up?
Not quite.
D looks like a little past that.
It is, but it's going to violate, right? Let's say that your clock width here is 10 nanoseconds, and your TSU is, let's just say 3, and your T hold is 2.
Oh, so that's supposed to be close enough that it is good.
So you're still in violation. So we don't know. And then here, this, like, I would make sure that this was clear of whether this is 2 or 3 nanoseconds or 4, right? Or at least within reasonable approximation, and say that, okay, it just makes the T hold, right? Or sorry, T hold is fine, it's the T setup that I have to worry about. So if this is 3 nanoseconds, I'm fine. If it's anything less than 3 nanoseconds, I still don't know. So let's say it's exactly 3 nanoseconds, then we're gonna clock in the data, which is back to 0, clock in the data. This is easily fine 0, right? So that's a perfectly fine question to ask, is these timing diagrams. There's timing diagrams like this in the homework that is due the day of the exam that you should definitely do before the day of the exam.
The hour before the exam. Fine.
I just walk in, you're like, and submit.
Just freshen your mind.
So on this exam, I don't think I have to do this to you guys, but I went back and I pulled in K-maps again because I was very disappointed with the last K-map performance. So I made them suffer, but you could see a K-map show up. Again, this is name of processes. This one has some questions about the fast carry adder, right? So we talked about the ripple carry adder, which is the just string full adders together. Then we have the fast carry adder, which is where we built the AND and NOR gate network in order to calculate the carries ahead of time, right, in order to make it faster. And so this has some questions around the propagate and generate functions that we talked about, right? With either it can propagate it one through or it can generate a carry on its own. And you might just have to answer some conceptual questions about this one. I'm not going to do the questions that they have on here. It's a little bit more complicated.
Could you refresh on the generate?
Yeah, so generate's really easy, right? Generate is as simple as if I have a string of numbers that I'm going to add together, and I design logic that can look at all of these ahead of time, right? Because that's what we're doing. We're looking ahead. It's carry look ahead adder. A generate statement is literally just, so if I call this index 0, 1, 2, 3, and A, B, then the generate is pretty easy, right? Because it's literally, you can just say, well, A at 3 and B at 3 is generated, right? But it ends up being a little bit more complicated than that, but that's basically all the generate is doing is, does this column generate a carry? And then propagate is, can it propagate a carry, right? Which is determined by a combination of, is there at least one in this? And if I have a carry, will it, right? The propagate is just saying it could possibly propagate something. And those equations that are more explicitly enumerated in the book, right? That has that like P3, P2, P1, P0, P0 or something like that, right? That's just one of the terms that's saying if it generates a 0, it can propagate. I don't think it needs P0, does it? Propagate through 1, 2, and 3. Okay, thank you. And then this one is, actually, this is a pretty good question. I forgot about this one. I give you a picture of 2 different devices. I call one of them a counter and one of them a shift register. We haven't really talked about shift registers very much. I did mention them, but a shift register is what it sounds like, is that each rising edge of the clock, it takes them and just shifts the values over, so that if you imagine a register, right? This is a register. it stores values in it, and I tell it to shift, it just moves them over. So this, and say we'll shift left, for example, this one gets thrown away, the 0 comes here, this one comes here, this one goes there. And now whatever is put at the input of it can get shifted in, right? That's a new value. That's all a shift register is doing. It turns out they're really easy to design. In fact, how would you design the shift register? What would be your basic element? Yes. You can do it with a mux. Yeah, this actually does work just fine with a mux. This also works just fine with the flip-flops.
With the flip-flops, it can only shift once per cycle. With the mux, you can send a
Yeah,
you
because
can send I don't know if it's asynchronous, but you can do it
A
you can do a
shift,
3 shift in 1 clock cycle, right? With the mux.
and so these questions are pretty fair because again, it's open note, open book. So even though we haven't covered them in depth, it shouldn't be right. We had two right answers, both of them. The DQ flip flop is really as simple as hook up the clock and I built a shift register. Right, because the clock hits, whatever's the input gets stored here, whatever is here gets stored here, whatever here gets, so on. I built a shift register. That's why it was a fair question, is because they were in the same state as you, but it was kind of like a, can you understand this? So basically, I gave you an option, is there's a shift register or a counter, write VHDL for one of them. I could also make you draw, like, here's this figure, draw me the block diagram of using the flip-flops or something, right? That's also a fair question. Yep. I think that's a fair sampling of the exam questions that you guys can expect, right? Timing diagrams for sure of some form, some questions that have VHDL and error code in it, some questions that are identify this code or write the code for a device that we've talked about. There's almost certainly going to be an identify these devices kind of thing. And then there could be questions about any of the labs or the project. Any of the labs we've had since the last exam or the project are also fair game. So make sure that you understand at least conceptually why we were doing things in the lab, right? Open notes, open book. You can bring a calculator. I don't think it'll help, but you can bring it. Does anyone have an only digital book, or y'all have physical? Okay, all physical. That's good. If you fall ill between now and Tuesday, make sure to send me an email before, because I can set up proctoring stuff for you guys. I don't want you here and ill, and I also don't want you to have to take the exam if you're in a hospital bed dying of COVID. But my advice is don't get sick, because it kind of sucks to, right? Delaying the time further down the line makes you forget more things, and then it just stumbles into like project 2, which we're going to start. Nope, not next week. Next week is a lab, cool lab actually. Anyways, it's like 2 minutes ish early or whatever, I forget. But
Toggles you don't need.
I
like basically because the toggles that kind of do it for you.
yeah, so I use so 0, 1, 1.
There's a lot of stuff on it.
I think it'll be okay. I think it's okay.
Gravity is
Like 0, 0, 1.
Like you missed that one.
Let's say call this our. This is going to be our most significant bit, right?
Yeah, it was
So
straightforward.
1, 0, 1.
No, the other one. Are you talking
Yeah, that
about
was
6.6?
It might be the
You need it with the
enabled version.
D. Yeah, you need it with. You need the before with the D. The state.
Dude,
It doesn't just toggle on
doing
its
the homework. I was
You
like,
need it to like change each time. You know what I mean? Or it just all. It just eventually gives you all ones.
That's exactly what I did as soon as somebody started saying that.
When you were grading labs, my first labs that I turned in were corrupt.
Mason Jordan.
So I resubmitted them, and they aren't all corrupt.
Okay.
Oh, yeah.
I can an app on my phone. I don't know if that's like scanning them, making progress.
Oh, let me stop this recording. I don't think they should.